Okay, thank you very much for the invitation. I'm very happy to speak in this session. So this is, well, there are two words here in this talk. One is together with Bramila Paz, Mata Gutierrez from Mexico, and Peter Neustadt from Liverpool. And it's an old result from 5 years ago, more or less, where we were studying this problem of Butler's conjecture. And recently, I got to talk to Soheila, who works in Imperial London. She's an expert in stability conditions, and I think my big merit is to convince her to work in this problem, and hopefully we will get something out soon about this topic. So this is the story. Well, let's start with the basics. I'm going to work on complex, smooth projective curves, C of genus G, and I will consider vector bundles on this curve. For the rest of the talk, this data is fixed, so the rank is n, degree is d, and I require that they are globally generated by this subspace of sections here. Yeah, and I denote this subspace of section of dimension. I started badly. Well, here is m, but later want to change. Anyways, so the fact that it's generated by the global sections or by a subspace of global sections means that this map is surjective by the evaluation map. So it naturally comes with a kernel, called kernel bundles, also called Lassercell bundles, or there are many names for this. Typically, Lassercells have nice results on this type of bundles. So it is very natural to ask, whenever this vector bundle is stable, is it true that the kernel bundle is stable or semi-stable? Okay, so what does it mean severe stability? So recall that a bundle is stable or respectively semi-stable if for any subbundle there it satisfies that the slope, this is called the slope of the sub-object is strictly less in the case of a stable and could be equal in the case of semi-stable. Well, you have always these two options, and this is called the slope. So this slope, well, this comes from the GIT theory. So we need this notion of stability to construct the moduli space of these objects. We have a nice structure of projective variety or algebraic variety. So this is from GIT construction. But it's also relevant that every time you have this globally generated vector bundle, it gives you a morphism, so it's a way of mapping your curve into the Grassmannian. You see? So for each point on the curve, you can associate the fiber over this point, which is going to be inside of yeah, it's a fiber of, I'm not sure if the numbers are there, correct? But it gives you a map into the Grassmannian, and conversely, every map from C to the Grassmannian, it can be seen as a pullback of the pullbacks will give you this one. Okay, this is one direction. Another direction. So why to study these kernel bundles? Because they have a consequence for the higher rank Brill-Netzer theory. So I don't know. I'm probably here. Most of you are familiar with the Brill-Netzer theory. Probably not. So I'm not assuming anything. Let me recall briefly what is this about. So over a curve, we consider this variety, the variety of all linear systems of degree D and dimension R, projective dimension R. And you can define the Brill-Netzer number as this number here, this very famous number. And it's very relevant because this number, the Brill-Netzer number, governs the existence of this variety. So this is a very famous theorem by Kent, that on a smooth curve of genus G, with DL is 1, RL is 0, when the Brilliant number is positive if equals to 0, this variety here is non-empty. Okay, and this holds for every curve. As this is not empty, in particular this variety, so I'm going quickly, but this is the space of all line bundles of degree D. I put it on this, yeah. Is the D doors should be down and they are up. Anyways, it's also non-empty, okay? On the other hand, if the real number is negative, so you can say that for the general curve, this space is going to be empty, okay? So it's very clearly, so the relevance of this number, I hope. And this is also famous by Griffiths. And there, after that, this is the existing problem, I also, there are many other results and brilliant theory about when this map is, this variety is connected, when it's smooth, and so on. Okay, so, so where we, well, is this, you can consider some moduli space of all the linear series of, but you can, yeah. Okay. Well, so it's good that I recall this part. Because what I'm going to do is a generalization of this. So it's what we call higher rank brilliant theory. So we want to have, the goal is to have some similar results. Instead of looking for linear series, so these linear series are so line bundles. So I want to go higher rank for all the vector bundles and replacing the linear series with subspace of sections of the vector bundle. Okay, so the generalization of the linear series is what we call it the coherent systems. So what is a coherent system? Is a pair of a vector bundle of rank n, degree d, and a subspace of section. Here I change it again. Oh, okay. K, subspace of section, the dimension of the space of sections here, V. And we have also notion of subcoherent systems, sub-object, which is going to be a pair, F and W. So F is a subbundle of E, and the W lives inside of the intersection of the sections here. Okay? And then for coherent systems, the notion of stability is not fixed. It's a notion that depending on a real parameter alpha. So, and we are going to find the alpha slope like this, in this way. Now I'm taking into account the subspace of sections, and we introduce a new parameter, real alpha. So in principle, it could be anything, but actually it makes sense only when this is positive. Yes, and similar as in GIT problem, you have the notion of stability. I mean, I'm saying things that they are, you know, well known, but I'm not giving many details. You can construct a modular space G alpha, depending on alpha, with these parameters of all sided coherent systems. So it's again, it has a nice structure, it's a quasi-projective scheme with a natural completion to a projective scheme. So with the tilde, when I'm referring to tilde, is the semi-stable objects. Okay. Okay. So in particular, we are extending the notion of the moduli space of, this is the moduli space of stable vector bundles on C. And whenever you put, you forget the subspace, you don't have subspace, it's just the moduli space. So I am extending the problem. Okay? So, questions here? I hope I'm not saying anything to, okay. So I want to give the picture of how do you think of these coherent systems. So you can say, okay, I have moduli space of coherent systems for every alpha real number, but actually it's simpler than that. You can compute what we call the virtual critical points, alpha E. So is this a purely numerical condition for this K, the K primes between the numbers, the given numbers or the here and the K, and that refers to the points where the stability of the vector bundle change, could possible change, not necessarily change. Okay, so and you have finitely many of these critical points. Yes, it's this space, and for every alpha in this interval, the corresponding modular space. So they are all isomorphic here in this interval, because the notion of stability is so the same, doesn't change. So the objects stay alpha stable for all alpha in this interval. So essentially, you have finitely many, essentially different modular space. Not so. Okay. And then, so what is the relevant one is the first interval, because here's for, I call it G0 for alpha small. So it has the property that every time that you have something stable, it's also alpha stable for small alpha for every k. Yeah. So because it's so the alpha is so small that it doesn't change the stability of the. On the other hand, you start with some pair here in G0, and you forget the subspace of section. You get something that's always semi-stable. So from stable, semi-stable. You can lose a little bit on the stability. So the point is, this is the space that is interested. Okay, I haven't defined this B. I'm going to define, but this is the space of this part is going to be relevant. On the other hand of the spectrum, the philosophy is that the space here for GL is the last modular space for alpha big. These are modular spaces that are very simple to describe, and very simple to say if it's non-empty or not. So this is, then people who studied this, I'm going to give the reference at the end, prove, okay, maybe, yes, okay, I want to define, yes, the aim is to be able to say when this Brill-Netter loci for higher rank is non-empty. This is the main goal. So, and associated to the Brill-Netter number rho, we have also a version for higher rank vector bundles. This is beta, yes. And this is the expected dimension of the modular space of the Brill-Netter loci. Okay. So what is known is that every reducible component here, it has at least this dimension. And I forgot what I want to say. Right. So this is about the structure of these modular spaces, G alpha and dk. And when yes, this is the dimension is theta at this point. Yes. So the smoothness of the modular space is controlled by, it is the same as in a linear bundle case, by the Petri map. Yes, it's when this map is injective, the multiplication of sections here. And actually, you see this part of the number is the dimension of this. So, and this is the tangent space at the modular. Okay. So not every curve has the condition that this is injective for every L. So this is a condition that can be also done for line bundles. In the case of line bundles, we say that the curve is Petri if this map, the Petri map, is injective for all line bundles. And this is a condition that that we will need later, for stating the theorem. So it's very well known that the general curve is going to be Petri. Right. Okay. Okay. Now, so I'm going to define different types of subspaces. For NDK is always fixed. So U is going to be the pairs that are in the last modular space in the GL coherent for alpha very large, such that the E is stable. What? The US is this pair such that it's going to be stable for all alpha, for all positive alpha. So there will be those who stay stable along the whole line. And this condition is a necessary condition to have non-emptiness on the moduli space. Okay? So the questions in this topic is, well, many questions, but the very basic question is the non-emptiness. So you want to study smoothness, reducibility, and so on. First, you have to check when when do you have objects. Okay. So when your parameters satisfy the necessary condition, is that non-empty, or is this non-empty? You know, if there are vector bundles at coherent system that stays stable for every alpha, it's also non-empty, or is on something that is stable and remains stable also all the way. Okay, and so the first expectation, the naive expectation, is that just as in the case of line bundles, that it was governed by the Dirichlet number, is that if this is positive, that should be true. But this is why wrong. I mean, we have many examples of this doesn't happen. Okay, also on the other direction as well. It could be it could be negative and have non-empty, or it can be empty and have positive. So, yes, please. I think so. It holds for genus 1, but it's like a slightly different theory. But in this talk, assume genus 2 at least, just by uniformity. But there are rare results. I mean, this theory exists also for elliptic curves. It's a little bit different, but it's, yeah. So as I say, all what I'm saying here about coherent systems, if you are interested, there are a series of papers by Brownlow, Garcia Prada, Mercant, Munoz, Newstead, and Teixeira on her own. Teixeira is also, she proved existence in many cases. And it's not surprising that when you assume that the degree is big enough, this is not going to be empty. Okay, this is the expectation. But okay. Okay, now tell you about Butler's conjecture. This is the topic of the talk. I apologize for awful notation. Yeah, don't you get confused, just to let me know. So I will define this space S. So these are pairs in the modular space of coherent systems. So K before is the sum of these two, because I am yes, because you know this n is the rank of E, and in order to have this surjective, I need at least n plus 1 sections, not n plus 1 sections to generate that. So so V is at least n plus 1, so I take n plus m. And I write it as a sum because the kernel bundle want to have rank m. So I'm going to get something from rank n to rank m. This explains the notation. Okay, and I put S0 when the alpha is small. Is for the coherent system in my first modular space. And Butler's conjecture can be stated as follows: that when the curve is general of genus G, let's say genus of this 2, all these numbers are positive integers, and also for the general pair, so this is also general in as you know belongs to an open Zariski open set of this space in this sense. You can associate to that what we call also the dual of this pair is just take the dual, this is the dual of the kernel bundle, and the dual of the, well, as a space of section of this bundle. Okay, you have to dualize your exact sequence that I wrote at the beginning. So this is Butler's conjecture. So when you, may I, wait a minute, yeah, sorry for that, but I think it's clear here. So from this exact sequence, so every time this pair E of V is alpha stable or some notional stability, when you dualize this exact sequence, this bundle is going to be dual here, and you will have the same number of sections also here, the duals. Okay? And the point is that this Butler conjectures has relevance for the Brilliant theory because I will be able to create new coherent systems with this number of sections by duality. Okay, that's right. And Butler also says that these two spaces that relates by dual, I see the typo. This is an M. Yeah, this should be an M. They should be birational to each other by duality. Yeah? And yes, it's N and M. I was checking because these numbers, but yes. Yes. Yes, there's an involution. You go back, yeah, you come back, yeah. Right, the difficult part is to show that this element is stable for small alpha. And when you are in the small alpha, as I said before, you have a projection of the Brilliant locus on the model space of vector models. Okay, right. We call that Butler conjecture because Butler was the first to prove some cases of this. He did it for a E semi-stable when the degree is big enough, bigger than this bound, and he also considered the full space of sections. You don't need all the full space of section as a semi-stable. And yeah, if you go without the equality, you get also stability. Okay. And we proved together in this paper with Brambilla, Mata, Gutierrez, and Newstead that a necessary condition to satisfy the Butler's conjecture is that the pair, it has to be alpha stable for all alpha. So if there is any chance that it satisfies the Butler's conjecture, this pair should come from something that survives all the passage of the alpha stability. And this is a very important notion, this survives the stability. We will see later. Right, so, okay, so a little bit more a piece of information. We call it T, the subspace in a zero where actually the Butler conjecture holds. That's all. Okay, now let me tell you the result. Again, it's a very, I'm sure there's some mistake somewhere on the, but let me explain you what is known for Butler. So Butler's conjecture is fully known for line bundles. It's not surprising, line bundles. So when the rank is 1, D, and you put here, yeah, M plus 1, here's the rank. And Villapaz and Newstead. But even so, this proof, it builds up in all the results on bundles on K3 surface, curves in size in K3 surface. So it's very, it's complicated. I mean, and it requires calling all the results from other papers. Larson and Farkas had a very nice proof as a consequence of some degeneration methods that they do. And this is very nice. This is just a consequence of some other problem. And we were very courageous enough to attack the problem for higher rank. And this is our best attempt. This is what we could say in this case. For these numbers, when M is these values here, and D is still, D is still big enough in these cases. Well, all the spaces coincide. You don't have anything new here too. Also, the Brilliant locus is exactly all the stable coherent system for alpha stable small is the Brilliant locus. And in this case, this is an isomorphism. Okay, I here put it correct, M and N. This is an isomorphism, and when I say it is non-trivial, I mean this space is non-empty. It's non-trivial. There are things that happen. Okay, and for non-empty hyperelliptic, again, for these big numbers of this type, we could conclude that this is irreducible. The Brilliant locus here is non-empty, is inside where the Bottomless conjecture holds, and if the Bottomless conjecture holds, it's inside of this S0. Okay, and non-trivial. I hope I know too far. Okay, so, and then we specialize a little bit more. In the case, a rank to vector bundle, T. And in this case, we could, that's the part I find personally interesting, because otherwise you don't see all these numerics, why is working, where doesn't work. And here at least we could single out a condition where it doesn't work. The condition is this one. So you can look at the pairs in S0 to T4 such that the pair admits a subpencil. So a subpencil means that the rank to vector bundle has a subplane bundle with two sections. That's a subpencil. And the two sections will be here in B. So it starts to be a little bit geometric, but very, very slight. So with this condition, we could prove that if you pick a D between an integer in this range, doesn't matter, it's just the range it works, then the locus of the Bottomless conjecture hold is exactly the complement here in S0 of FP0. So precisely those have no subpencils. It's pretty nice. And it actually is non-empty. So this is a it's non-empty. The dimension is smaller than the Brin letter. And for these D's, we could prove Bottomless conjecture for those values. You can compute, there are values there. I mean, I'm not saying, I am not saying an empty condition. Some integers there. And moreover, if the D is big than this bound, the dimension is precisely the Brin letter number for. And well, okay, and I can also conclude that the T is small. So, how much? 15 minutes? Okay. So this is the easy part of the talk. I'm sorry. And we work a lot. The techniques are not very insufficient for this. It's really very messy, difficult. There was no idea of what should be. I mean, first of all, it's true, or what should be the thing that's not true. So. So we have, together with Soheila, as I said, I convinced her to look at this problem because I was convinced, yes? Yes. We said something on non-hyperelliptic. If not, it works for a general curve. This is for general curve.
Yeah, my question is, if, so the conjecture, if you prove it for one complete curve, and use the result for a general curve?
So instability is an open condition, yes. But yes, but you have to make clear what does it mean specialized in this case, because it's, you want to specialize the bundle and the kernel. You see? So it's not clear how to state it, but it's true that the semi-stability is an open condition. Yeah, might be a way of doing, yes. Yeah. Okay, so with this new approach, well, it's all very different. To start with, we had to extend our objects to triples. So, yes, I started with some morphism like this, right, here. But now I can allow to be torsion sheaves are more general, and this morphism is not necessarily subjective. So we're just to work with triples like this. And this category of triples is an abelian category, and we are going to work also on the bounded derived category associated to this triple. Okay, so the objects now looks of this way, and well, okay, here is a couple of definitions. What is a torsion object? So there also the rank is 0, and we can associate it to this triple, the torsion part of the triple, which is the definition, and the quotient with the torsion finds a torsion-free object. So from here now on, it's all categoric, and I won't have time to, maybe I'm going to skip. So we have also a notion of a slope function, yes, of this triple, just as before, the slope. And we are going to call it semi-stable if, as before, all the sub-objects are smaller or equal to that. Okay, so I'm going to say roughly what is happening in this category. Yes, it's going to be semi-stable if this is injective. So this condition means that actually you have this number of subsections, n, in H0V, because that was not imposed from the beginning. And you have, for every object, you have also a Harder-Narasimhan filtration into a semi-stable object, and you can have, you define the mu, the maximum slope appearing in the Harder-Narasimhan filtration. So this filtration helps you to truncate the objects, in the category. I am really aware that this is a little bit too technical, but there is a way in this business of stability conditions that you create. First, you construct your T-bundle structure, and in this case, we are going to define AB, the hardware bundle structure. Quickly said, is all the objects complex in the category that looks like this, and such that the kernel is has this is given by the B. So the m plus of the kernel is at most B, and the m minus in the co-kernel is at most under minus T. So this is essentially the building blocks of your derived category. Yes, it's not so relevant. So the numerical Grothendieck group of this derived category is given, it's a tree. So this is what you call the character of any object. So it's a single out the invariance of our object. It's the rank, the degree, and the number of sections. So here is the notation from, this is notational, from the right categories. But essentially, you are taking the rank of V, the degree of the vector bundle on the character, just as before. So for any pair on the complex number or on the real plane, you can define a function which is actually an homomorphism of groups from this numerical Grothendieck ring group into, I don't know why I put C or, well, this is typically C, okay? And this is the, how do you call it? The charge, the famous charge, okay? So you define, yes, in the complex numbers, a function like this, yes? So you have all your parameters there, K and B of W is given, and that is going to be a stability condition. So stability condition, it's a pair, so you prescribe the heart of your structure, and you give this function. So this is something you have to be proved. Actually, it's a Brisland stability condition. Now, so, okay, here it starts to be a little bit esoteric. I claim that it exists a piecewise opera semi-continuous quadratic function gamma, such that if the B is 0, the gamma B is 0. So the graph of this gamma is in the real Earth R2. If P is at least 2G2, then you have this condition. And in between, so everything that is slope stable, rank n, so with this slope, then the quotient of the number of section n is less or equal to gamma, the gamma of the n, okay? And I will call U gamma all is a little bit the complementary of that. I think everything is clear if I see you the picture, because otherwise you are not good. So, so this is what I call the brain letter curve. You have this curve, yes. The last condition is actually the Riemann-Roch line for I'm sorry, it's really so. As you'll see, you have two coordinates here. So let's check first the coordinates Dn and Kn. Yes. Okay, I will come back because I need to explain something. Yeah. So this is the U gamma. U gamma is the yellow part in the middle. So I claim every time you pick a point in the U gamma, it's going to associate to that an stability condition. Yes? And this brain letter curve also at the same time tells you, give you some information about the stability of the vector bundle with these coordinates. But it's a little bit confusing, a lot is confusing, because I have 3 parameters and I am dividing by the rank each time. So this is a projection into R2. Okay, so I'm playing 2 things in the same plane. So one side you have a notion of the stability, on the other side, also inside the same plane, you can describe a family of a 2-dimensional family of stability conditions parameterized by this. Okay, and this is I find this is the key point. This is the key point of the whole thing. It's what I say. You can plot both the plane, the plane of the parameters of the stability conditions simultaneously with the image of this projection map. Yeah, the character of this is the character of a type of vector bundles that you have to divide by n. Okay. Now, for each non-zero object on the heart, yes, of this class, we define a new notion of slope. So the stability condition comes with a notion of slope, yes, like this. Just as is the quotient of the real part and the imaginary part of this charge function, like this. And okay, are some definitions here. Yes, I hope I put. Yes. Yeah. This has to be done in the category, so you have to shift by R. But I think I want you to keep in mind this key point, that you are plotting both in the same place. And so the advantages of that, that you can construct the Chandler structure out of there. So, oops, sorry, let me go back to this. So you fix your character, you make the projection, and this projection is not on U gamma, it's in the complement, yeah? So for this, is this point here, so it points here. So this yellow is an open set of stability conditions of the category. Every point here represents, and in the other hand, you have the projections of n here. Okay, and you have a finite many of lines, so these segments, yeah, we call it the wall crossing that I think you have here this concept. So there are lines that goes through the projection of the character, and if the rank is 0, well, the lines are parallel to this slope. And an important thing is that, you know, everything that is between the chambers, it doesn't change the stability. The things remain stable. You see, I will try to convince you what's going on here. So I will first explain you about alpha stability. It is a real parameter, and you have the changing of the stability in a real. So what we're doing now is unfolding these stability conditions in a 2-dimensional. It is also fake unfolded because you don't have 2 parameters. There are 2 parameters, but what it counts, 2 parameters, but what it counts is the stability conditions. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters. So you have 2 parameters, but you have 2 parameters So just to put it in relation with the other concept, is the slope. So actually, in reality, this stability condition varies on one parameter, meaning the slopes of these lines. So before I was dividing into intervals, and now I'm dividing like a cone like this. Yes? This is the reason is that because there is an action of LGL2 on the space of stability conditions, and in the end of the day, for my objects, is one parameter stability condition. This is known. But here we are extending a little bit, consider two-dimensional parameters, because this picture for me is crucial, because we are hoping, so this is very geometric. There is a way of connecting, so there is a way of, so you can read when the kernel will not be stable out of your picture. The important part is that this spring letter curve is not fixed. It can be improved depending on the curve. And this is something we are working on. We can give a general statement for every curve, right? But maybe the bounce is not good. Or you can improve the green letter curve here a little bit up and say, oh, all this is happening. Yes, so, okay. Right, so here he explained what happens in the chamber, so yes, how do you destabilize the objects. So this is very much in progress. I think it's going to be 2 papers. So Helen is going to write a 60 pages paper just on the setting of the triples and the categories, and a second paper on the consequence for the Butler's conjecture. But I just want to present that I like very much this type of, so now I have a better understanding of what does it mean to have the Butler's conjecture to hold in a more geometrical, in a more visual way. Yeah, it can be read from this chamber's construction. So yes, I had another slide, but this is just the relation with the stability. And this is all. Thank you very much. Yeah. Yes, yeah, you're right. This is inspired by so Hela has a work on stability conditions on K3 surfaces, and then you have 2 parameters. Yes. So you are asking for geometric?
Yeah, like for instance, like the fair factor of this, factor, the homology or
Yeah, I should think about it. I don't know.
Are you trying, like is the idea of the project to try to realize this wall crossing that you have with alpha as a wall crossing of the bridge?
Yes. This is the idea. This wall crossing. So for when you don't have walls, you expect to the Butler's conjecture to hold, but they had to figure out where does it happen. So now it's a game of numerical game. So I want to find the right numbers, but this is delicate because I'm working with quotients, and so rational numbers, and I want to do something about the integers. So it's a delicate game there, but I'm sure we can give a clean result or say, okay, this geometric range, Butler's conjecture holds. Yeah, this is the hope. Yeah.
Cambia igual. Y este tiene una pinchita.
Como foi? Quieto. Richard.
No, sería maravilloso.
Podemos partir, ¿no? Como quieras, cuando quieras. Eu estou aqui.
No queda un minuto.
Está frio.
¿Está frío?
Está frio hoje. Como ayer. Não? Tu está acostumbrado. Não. Não. Não precisa. Depois que eu abro, me esquento.
Okay, we're going to start with the second talk of this afternoon. So now we have Marco Pacini from
University.
UFI,
Yeah.
and he is going to be talking about on the theorem for graphs and stable curves.
So thank you very much for the invitation and for the opportunity to be here. So today I'm presenting a joint work with Alex Abreu, and this is also a work in progress with Nicola Pagani from Liverpool. And okay, so let me just start with some classical theory. I will start with the classical Torelli theorem for smooth curves. So for me, C will be a smooth curves of genus G over the complex numbers. And we saw in many talks in this session that we can attach to this smooth curve a Jacobian variety, which is defined as follows. So this is the H0 of the canonical bundle dual up to a lattice. And I mean, this is a torus of dimension G. And actually, it is more than a simple torus. It is a principally polarized abelian variety, and the principal polarization is given by the theta divisor of the Jacobian variety. So I recall that the Jacobian actually is can be described as also the variety of degree D line bundle, or maybe in degree zero line bundle up to isomorphism. And when we look at the degree G minus 1, it's pretty nice because we can give an incarnation of this theta divisor as this variety of the line bundles of degree G minus 1 having a section. And so I'm going to consider this Picard variety as the main object for this talk, and this is the divisor I'm going to consider. Okay, so the classical Torelli theorem is, can be stated as follows. If we have two Jacobians with their theta divisors. If they are isomorphic as principally polarized abelian variety, then the two curves are isomorphic smooth curves. So this is a very classical result due to Torelli. And we also have a modular formulation of this result, which goes as follows. We can consider the modular space of smooth curves of genus G up to isomorphism, the modular space of principally polarized abelian variety of dimension G, and we do have a map, the Torelli map, associating to a curve is Jacobian and theta divisor, and so this map is injective. This is the statement which is equivalent to this Torelli theorem. So far so good. And what we want to do now is to look at singular curves. So we saw that in the previous talk and gave a generalization of this theory to higher ranks, but there is also another natural direction, which is the direction of singular curves. This is quite natural because we do have a modular space, very famous modular space of stable curves. So what is a stable curve? I recall that a nodal curve is called stable if every smooth rational component of the curve intercepts the rest of the curve in at least 3 points. This is equivalent to say that the curve has a finite number of automorphisms. And it is semi-stable if it is greater or equal than 2. So I'm trying to extend the setting to singular curves. So if you recall, I recalled you that the Torelli maps goes from mg to ag. So on one hand we have mg bar, and actually this is a nice space. It is a projective space, a projective scheme. This is a quite famous theorem due to the linear Mumford. But what can we do with the other part of the map, of the Torelli map? So we compactified mg. What we can say about the target of this map? So to do that, we have to first of all talk about compactified Jacobians, because the Torelli map associated with a curve is Jacobian. So what is the Jacobian of a singular curve, or more precisely of a nodal curve? So this is a highly non-trivial problem. So I recall you that we have a universal setting. So over mg, you can consider the modular space of all degree D line bundles on smooth curves, but still this is not compact mg, so neither is this compact. So we look for a compactification of PDG, which is this universal Picard-Schivo over mg, but a compactification that goes over mg bar. So something that completes this diagram. And so Lucia Caporaso did this step in her PhD thesis. And so I can state this theorem as follows. There is a modular compactification of PDG over mg bar. And this modular adjective here means that the objects of these compactifications have a geometric meaning. So I'm trying to explain now what's the modular compactification we have in this diagram. But in particular, looking fiber-wise, we get a compactified Jacobian for every stable curve. So this is the natural object we can look at when we try to describe a Torelli map for a singular curve. So a singular curves, I will associate in a few moments this compactified Jacobian as a target of the Torelli map. But what is this modular compactification? To give you a concrete description of this, I need to look at some more definitions. So first of all, the smooth rational curves on a semi-stable curves is said to be exceptional if it intercepts the rest of the curve in 2 points. So recall that it is at least 3 to be stable, but the semi-stable object has some exceptional components that intercept the rest of the curve in 2 points. And it is called quasi-stable, a curve, another curve, if the two exceptional components do not meet. And so we have some stability condition here to talk about compactified Jacobian. So I need, as an object, I need to take all quasi-stable curves and some line bundles on the quasi-stable curves. So these line bundles that are selected through a stability condition goes as follows. The stability condition tells you that there is a numerical condition that is encoded by the numerical invariant of the curve and the line bundle. And this is actually the main basic inequality that we need to talk about stability conditions. And so take this condition as, okay, I'm selecting some line bundles on all quasi-stable curves. Is a way to select the degrees of the line bundles on the quasi-stable curves. And in fact, this modular compactification of the Jacobian goes as follows. You take all the quasi-stable curves over a stable curve. So see a stable curve, you have all the quasi-stable curves you can consider over C. Over means that you can remove a node and replace a node with an exceptional component. So you take all the quasi-stable curves over a stable curve, and all the balanced line bundle. Balanced, I recall you, that is the ones that are selected through a combinatorial condition. So this is the modular description, and in here there is also an equivalence relation, which is highly non-trivial, because, okay, this is, I don't want to explain really in details, but these equivalence relations is telling you that two objects here can be identified in the modular space, and are identified if and only if their difference is a twister. A twister means that you are only modifying the line bundle via something which is the limit of trivial bundles. And actually, these twisters are the responsible of non-separateness of the Picard functor. And but okay, if you take this into account, you get a modular space which works over mg bar. And so this construction, by the way, is got via a GIT construction. So you can describe the objects in this way, but it comes from a GIT modular construction. And actually, this modular space is fine if and only if this condition, numerical condition, holds, which is equivalent to say that this equivalence relation is trivial. So when this equivalence relation is trivial, the modular space is fine. Otherwise, we have objects identified in the equation. But look, we are taking d equals to g minus 1, so this is exactly the 1 degree for which this equivalence relation is non-trivial. So we fix d equal to g minus 1. And as in the smooth case, so recall that I'm trying to extend the setting, the original setting, to singular curves. So what we can do, we can take the theta divisor. So the theta divisor has this description, again, as in the smooth case. And actually, there's a theorem by Bouville telling you that every component of this, which is a priori a subvariety here, every component has the right dimension, has dimension g minus 1, is a divisor. And more than that, Alexeyev proved that it is a Cartier, ample, and has just one section. So we do have a pair okay, that looks like a principally polarized abelian variety. It's not quite the same as a principally polarized abelian variety, because J of this variety is not smooth, for example. You have to enlarge your category, and actually the right way to say that is that this pair is a principally polarized stable semi-abelic pair. I don't want to give the semi-abelic pair. Abelic, not abelian, abelic. It's something quite general, but I don't want to go to the right definition. I don't want to do that because it's out of the purposes of this talk. You can understand the talk without knowing this. But I mean, we have a problem. So take this pair. I gave you the description of this p bar of the theta. This is an action which is needed in the setting of this. This is the Jacobian, the degree 0 line bundles. Can this pair reconstruct the stable curve? This is the equivalent question as in the smooth case. And very quickly, we do have a modular formulation for this question because Alexeyev constructed the modular space of these objects. This very quite difficult spelling objects, and he proved that actually we do have an extension of the Torelli map from mg bar to these modular spaces, a modular space taking C to this pair. And so the modular formulation of the problem is Tg bar injective. Mod is modular, is because you do have many compactification, as you know, and this is the modular compactification. Is Tg bar injective? So the answer is no, and the talk is over. No. No, it's clearly not. Why? Because we do have curves intersecting at the separating node, and the Jacobian are the product of the two components. So it's clearly Torelli in this sense fails because you don't have the way to reconstruct the point of the intersection of the two curves. So it's clearly not, but how you can describe the fibers, for example, of this map? This is the natural question we want to answer. And let me just, so as a, for the perspective of this talk, yes? A few? Sorry?
Like, is it normal?
Yes, it's not reducible. It's not irreducible. It has a main component containing the locus of the Jacobians, for example. I don't know if it is known that it's normal. I guess, I don't know. There is another modular space, this Voronoi compactification that goes to it, but it is not known if it is normal. The other one is normal, I guess, and so I think this is not known, but I have to check. Sorry? No, the main component containing the locus of the Jacobians. Yeah, the whole one is not, of course. Thank you. Okay, so by the way, this is the component, because otherwise the map, the fibers could be empty also, in a way. Okay, and so let me give you the answer gave by Caporazzo and Viviani to this problem. So sorry, I'm going to be more technical now, but I hope that it convinces you that there is an answer, at least. So all the statements now are true combinatorics. So we can take the dual graphs of a stable curve. So the dual graph is the graph whose vertices are the reducible components, and the edges are the nodes. And whenever we have two components, so we have two nodes, and they are connected if and only if the corresponding node is inside the intersection of the intersection of the two components. And we also have to enrich the graph with the geometric genus of the curve. But we have a graph, and this is the main definition. In a graph, we can take these C1 sets. So a C1 set is simply a subset of the edges of the graph, such that when we take gamma modulo the complement of the S, the modulo means that you are contracting all the edges that are not inside S, we have a cycle. So sorry, I can draw a picture. But this is quite clear, this condition. You contract everything which is not in S, and you get a cycle. Normally, and then we have also another condition here. But with this definition, we can take C stable. We have the normalization at one C1 set, and we can also form all the stable curves out of these components you obtain normalizing the curve at the C1 set. So I normalize the curve at C1 set, I get very many components, I got the points over the nodes, and I can glue these components together in another way, maybe, and I can obtain many, maybe, stable curves, not only one. And I call this table of C. All the way you can obtain the stable curves by means of this operation, normalize at C1 set, and then glue together again. And so Caporazzo and Viviani theorem tell you that actually the fiber over this point is all the stable curves that you can obtain by means of this procedure. So in the case of the banana curves, the so-called banana curves, namely two curves attached at 2 points, you can either glue the two curves together at 2 points, or you can do the other way around, the other gluing. So these two curves, if the components are isomorphic, of course, you have two different curves in the fiber of an object. Okay? So this is a very clear and complete answer. So sorry, how? I think it's. Oh yeah, I have time. Okay, and now what I want to do is to present another compactified Jacobian, because my goal here is, okay, we have the setting, the smooth, the setting for smooth curves. We enlarge the setting to singular curves. I presented one possible solution through the Caporazzo's compactified Jacobian, but Caporazzo's compactified Jacobian is not the only one. It's not the only compactified Jacobian available in the literature. So we have also another compactified Jacobian that I'm going to present now. And so our goal should be, okay, can we give another Torelli theorem or the same Torelli theorem for this other compactified Jacobian? So for this, I have to consider another direction. So recall that the Caporazzo compactified Jacobian parameterized all line bundles on quasi-stable curves having some limitation in the degree. And now we can consider another direction, which is the direction of torsion-free rank-one shifts on the curve. And we say, again, that these torsion-free rank-one shifts are quasi-stable. Actually, P quasi-stable, P is a smooth point in the curve. If the same hold, they'll say, namely, we have some numerical condition, and also another condition that depends on the point, on the choice of the point. And I mean, you have to look at this condition as another combinatorial condition, selecting some degrees of the torsion-free rank-one shifts. And actually, there's a theorem due to Eduardo Esteves that I mean, you can consider all the P quasi-stable torsion-free rank-one shifts on a curve of degree D up to isomorphisms, and you get a proper scheme. Okay, this is another compactified Jacobian. Why I'm calling it another compactified Jacobian? Because this is a fine moduli space always. Okay, it opposite to the case of Caporazzo, where we saw that there is a condition to be fine. Here I always have a fine moduli space. And of course, they are isomorphic if and only if the Caporazzo compactified Jacobian is fine. But in this talk, we are considering D is equal to G minus 1. So again, it is the critical value where the two compactified Jacobians are different. And so again, we can consider a theta divisor for this compactified Jacobian. But we have some problems here because this divisor is not ample, as in the case of a Caporazzo compactified Jacobian. But still, we have a moduli space and the theta divisor. So the question, can we reconstruct the curve using J and theta? And I don't have the answer, sorry. But what I want to convince you is that Torelli theorem using this new moduli space should be different from the answer from the Torelli theorem given by Caporaso and Viviani. And why this? So I resort to a combinatorial setting. So I'm going to consider what is called the combinatorial Torelli, which is considered also in the work by Caporaso and Viviani. Why? Combinatorial is quite natural because this compactified Jacobians has a stratification. And these stratifications are encoded by a poset. And I'm going to describe this poset, I hope quite explicitly, and then we will pose the Torelli, the combinatorial Torelli problem I want to consider. So now everything goes to combinatorics. So I have to give you all the setting again. So given a graph, I can consider divisors on the graph. So divisors are simply functions going from the vertices to the integers. We have the degree, which is the sum of all the contributions, and we have the divisors of degree d on a graph. So sorry, I have to introduce some notation here. We can consider, given a subset of the edges, we can consider these two graphs. This one is obtained inserting a vertex inside an edge. So we have to insert an edge, a vertex, we obtain a new graph, and this other one is obtained by removing the edge. So the one with below E is removing, the upper one inserting a vertex. We consider, so we can restrict divisors on the graph obtained by removing. And the key definition here is the specializations of graphs. So this is quite important because, I mean, we will see later that this gives you the structure of a poset on a particular set. So, and gamma specialized to another graph, gamma prime, if the graph is obtained, again, contracting some edges of the graph. So this operation, we already seen this operation when I defined the C1 sets. So it simply say that you are contracting some edges and you obtain another graph, and this new graph is said to be a specialization of the first one. We can also consider, I mean, for any given divisor on a graph, we can consider the push forward of a divisor. So there is a natural operation going from the divisors on a graph to the divisor on a specialized graph. And the last thing I need is the notion of pseudo-divisor. So a pseudo-divisor on a graph is simply a divisor on the graph obtained by subdividing the graph in some edges and having some degree conditions on the new vertices we got. Okay? So pseudo-divisors reminds you the operation of passing through from a stable curve to a quasi-stable curve, and an exceptional component. So we are here inserting a vertex inside the edge. It's in some sense is the same. And we can, we can do all the theory we did before. So for quasi-stability, so this is again a divisor on a graph. We can consider a numerical condition. So this is the equivalent of the numerical condition that we gave to define quasi-stability for torsion-free when one shifts. So, and this works quite well. I mean, we have a graph, the divisor on a graph, a stability condition for divisors on graphs. What we can do now, we can consider this poset. So this is quite important for this talk. So I can consider all the pairs that are I mean, pseudo divisors, namely on a graph I can consider divisors on subdivisions on the graph, and we impose a quasi-stability condition. And why it is a poset? Because we have specialization. A specialization gives you a structure of a poset on this set. Because I declare that one object is greater than another one, if we do have a specialization that takes a divisor to another divisor. So this is quite technical, sorry, but I introduced this poset. Why? Because I mean, okay, a priori this depend on the point, on the vertex V, but it doesn't. Actually, we have an isomorphism of poset if we vary V to V prime, and so this is the final object we get. So this is Q D of G minus 1. So it depends only on the degree. So the V dependence drops. And now we come back, sorry for the technicalities. We have this poset. Why is important? Because we have a bridge between the algebra geometry and combinatorics that goes as follows. So we can consider the stratification of the compactified Jacobian. So this stratification is induced by the inclusion of the open locus of the line bundles on the curves, and we do have a stratification, and we do have a bijection between the strata of this stratification and the poset I introduced a few moments ago. And actually this is quite explicit. Actually the strata has a poset structure given by the inclusions. And actually, for any given C and I in a stratum, we can associate an element of this poset. What is this element? I mean, a torsion-free rank 1 shift. There is a structure theorem for torsion-free rank 1 shifts. These are line bundles times the ideals of some of the nodes of the curve. And so di here is actually the degree of the line bundle, the multi-degree, and these ei that are the subdivided edges are actually the locus where the torsion-free rank 1 sheaf is not invertible. Okay, I mean, we have a description. This tells you that we have a concrete description of the stratification of the Jacobian by means of this poset, which exists a priori as a poset, abstract poset. And the key observation is that if two Jacobians are isomorphic, then the two posets are isomorphic because the stratifications are the same. Okay, so we can pass from of course, algebraic geometry to a coarser setting, which is the combinatorial setting. I mean, the first step should be, can this poset reconstruct, for example, the dual graph of the curve? This makes sense because I start with two Jacobians, they are isomorphic. I go to the stratification, they are the same posets. And so the question is this poset, is it possible to reconstruct the graph by means of this poset? Of course, the answer again is not, because the graph has separating edges. It's the same problem we had when we had these two components intersecting at one node. But again, so the question, the combinatorial Torelli goes as follows: given gamma, what are the graphs that has the same poset as the poset associated to gamma? So can we answer this question? This is the combinatorial Torelli. Actually, you can do the same for Jacobian, for the Caporazzo's compactified Jacobian, and actually this is the first step that Caporazzo and Viviani considered in their theorem. And so the answer we got, and so we had this theorem. How much time I have? 8 minutes, perfect. So the answer we have is actually different from the combinatorial theorem of Caporaso and Viviani. And so our answer is the following. So a biconnected component of a graph is actually a maximal two-connected subgraph of gamma. I mean, if you have a graph, you can look at the vertices that separate the graphs into connected components. So these components are called two-connected subgraphs, and it is biconnected if it doesn't have these vertices that disconnect the graph. And we can prove the following, that two posets are the same if and only if the biconnected components of the two graphs are equal. So this means that you have a graph, you have this poset. This poset reconstructs the biconnected components of the graph. If the two graphs are obtained by attaching biconnected graphs in different vertices, these two graphs have the same posets. And actually, it is a theorem which is different from the one due to Caporaso and Viviani, the combinatorial theorem. So just a mention that similar result, we can work also in a tropical setting, but it's another story. And this result is different from the combinatorial Torelli of Caporaso and Viviani. Maybe I don't have time to go to the comparison results, but just to say very quickly in the last 5 minutes, just recall that I mean, we can consider also the stratification as we did for Esteves compactified Jacobian. We can consider the stratification for the Caporaso compactified Jacobian. Again, we can consider the poset of the strata. This is this new poset. And I go directly to the theorem of Caporaso and Viviani. This is the theorem they got. This is quite technical, but this is the theorem, the combinatorial theorem they got. And actually, I mean, it is different from our theorem. And if I can draw a picture, maybe the last 5 minutes, I can give you an example of two graphs that have the same poset of Caporaso compactified Jacobian, but they have not the same poset for the Esteves compactified Jacobian. So can I draw the last picture of the post? And, and in here I have these two graphs. So don't mind about these conditions. I'm going to give a concrete example of two graphs for which the two theorems differ. So the graphs are as follows. Just to have some idea of, for example, this one. This is biconnected because we don't have any removing vertex. But if I consider this graph, if I remove these two edges and I glue the two components I got together in a different way, in this way, so these two graphs have the same poset of Caporaso type, namely the stratifications, the poset encoded by the stratification of Caporaso's compactified Jacobian are the same, but looking at the Esteves compactified Jacobian, they are not, because I mean, these are biconnected. So our theorem tells us that the two graphs has different posets. So this is everything I wanted to say. Thank you very much for your attention. Yeah, no, but I mean, it tells you that the plurality theorem should be different because the combinatorial counterpart is different and it's finer actually. I mean, and so, yeah. We don't know. When you have two curves with the same Jacobian, we can't decide if they have the same step as Jacobian. It's subtle, actually. It's not that easy. But we believe that the stronger Torelli should be possible looking at this esteves. Our hope is that it reconstructs actually the curve name up to these separating nodes. We hope that this should be possible. Thank you.
Yeah, this is like a direct or
Is the my control
yeah,
from the
yeah. But you know,
line? Yeah, it is
for the audience, I don't need. But I don't need. You know, I have, I should have. Uh-huh. Okay, so okay, so just you know, yeah, it's going to be fine. Very good. Very good. I like this. You know, this is visible. Oh no, already. Maybe. Yeah, whatever. Temperatura. Yeah, it's like it's 70 degrees. 18. Let's make it 22. Okay? So I checked these computations with this filter group. So basically, it seems that this is not it's not 0 mode 16, and this is 8 mode. This is 8 mode 16. Basically, it's not 0. Basically, that's what I say. So this is exactly what you said. It's 8 or 0 a day, and nobody knows what's going on. And this is the case when you have odd number of lines and only even multiplicities. I have no idea, but you know, once you there is a chance to say something about this, you know, brewing procedure, maybe there is a chance to basically exclude the existence of potential Bow quotients. And now it's getting even more interesting, you know. because this is the last part of Hirzebruch's like work. Because you remember, you know, you can have like exponents for the Boolean covers 2, 3, and 5. So describe what's happening for the exponent equal to 3. So you have the dual Hesse and Hesse. For 5, you have this complete equilateral. And then for 2, there is like a sequence, infinite sequence of potential combinatorics that can lead to new Ball quotients. And he was able to show that some of those in this book in Germany. In German, yeah. This is written in German. This German book. So there's like a chapter strictly only about that. And since it's in German, you know, it's like, so at least with only even multiplicity. So you're supposed to have points of multiplicity 2 and 6. And the first case that Hirzebruch was not able to show was the case when you have 39 lines, 39 six tuple points, and 136 double. So if you just compute these numbers, you know, according, obviously not. No. You can basically plug this. We don't know the Chern slope, but you know, you cannot realize this over the real numbers because the Euler characteristic trick. Yeah, so if you just look this or use this Euler characteristic, you know, for real configurations, you can see that this is not constructible over the real numbers. So it has to be complex, if it exists. Now 20. Oh, here is nice. You can just warm a little. Yeah, it's like it's a warm up, like, you know, using this air conditioning. Does it work? Yeah, it works. In principle, you know, in principle, I don't need this microphone for the audience. I can. I think it works. No? Does it work? I see. I hear an echo somehow. Okay. If it's okay, it's okay. No longer. We changed the name. we are no longer pedagogical. Yeah. So I'm going to speak about rational arrangements of curves, mostly, and the so-called maximizing curves. So I would like to thank the organizers for inviting me to Santiago. It's my first time in South America. It was a part of the joke, yeah? And also, I will try to follow this local new idea that I'm going to work over the complex numbers. This is the new tradition. And also, Olivier, you know, introduced a new idea. And everything is going to be non-degenerate, basically. So, everything what I'm going to say. And this is like a meta question. So, how to use, or I think it dates back to Hirzebruch. So how to use arrangements of curves in some interesting algebraic surfaces to construct new examples of algebraic surfaces. So his idea was to use like line arrangements in P2 to construct new examples of Ball quotients, explicitly. So as you remember, there's like this famous paper by Delin and Mostov with hypergeometric functions, and there is like description how to use this hypergeometric guys to construct Ball quotients. But these constructions are not explicit, and I would say, sorry, obscure, yeah? So the Hirzebruch wanted to make it like visible, like you have equations, like you have like, you see how this guy is constructed. Yeah? So this was like roughly the idea, how to be explicit. And today I'm just going to follow somehow this idea, because for me today is to construct algebraic surfaces with high pickup numbers explicitly. And somehow this aim is like, you know, it's a very classical question. Yeah? So if you ask me how to construct these guys, there are two fundamental, or let's say, two classical approaches. So the first part is just look at smooth hypersurfaces in E3C, and this is completely open. Meaning that, like the expected, so if X is such a hypersurface, smooth. So rho of X, so the pickup number should behave like 2 divided by 3 times m to the power 3, where m is degree. Okay? And the best what we can say about this, like for m sufficiently large, is like we have examples with pickup numbers 3 times m squared. Okay? So this is the kind of gap that we have. Okay? So this is somehow hopeless. And then double covers. And double covers is basically due to Persian, and roughly his works 1980s. He was also, I think, in Talca, yeah, for in Chile, like 4 years ago. I don't remember exactly. So basically, roughly the idea is just to start with P2 and reasonable curve. Reasonable means with ADE singularities. Then take the double cover, resolve singularities, minimal resolution of singularities, and then check what's going to happen. So what is the expected pickup number for this guy? And I'm going to use this approach today just to tell you something, just to say something about the geometry of these curves. And I'm going to use also definition by Boville. And this is 2014. It's like, there's like a brand new paper about that. So if X is smooth, complex, projective variety, and then he's saying that X is rho maximal if the pickup number of X is equal to the naive bound, upper bound, which means that H11. Yeah, this is his definition. And I'm just saying my talk is about something not degenerate, which means that here he's also assuming that H20 is not equal to 0. Yeah, because this is somehow the case when the situation is non-trivial. And this is like, you know, his definition of these guys. So, and as you can see, this is for any smooth complex projective variety. So I'm not saying anything that I'm supposed to restrict to algebraic surfaces. Okay, so let me just speak about, right now, about Hirzebruch's, let's say, contribution. It's 1984, I would say. So basically, this is a very nice paper by Hirzebruch, where he's explaining what Persian is supposed to do. Okay? And now I'm going to explain what does it mean. So in this paper, he's saying the first, so what is the maximal possible bound, upper bound, for the pickup numbers of the double covers? This is the first question, yeah? So let x, so in this case, x is basically P2 over C, and he is assuming that C is a reduced plane curve of even degree, d equal to 2m, with only ADE singularities. Okay, then pi this is the double cover branched along C, and what we just say y-tailed is the minimal resolution. Okay, so right now everything is standard, and somehow he's calling this surface as a surface associated with this curve C. This also you can find. Okay, so, and we denote by row of y-tailed the pickup number, okay, so everything what I need is basically on the blackboard, and now I have to, okay, I supposed to switch the blackboard. It's not a very good idea. That was bad. But since everything is basically standard, let's say that as the first proposition, extremely crucial version, and I would say this is mostly irritable. And what he proved, so basically in the setting, I should say as behind, yeah? As behind, we have one is basically from the P2, then there is the magic number, total Turina number, I will just say in a second, and then this is Hipster with magic. This is 3, because you remember that I wrote that d is equal to 2 times m. This is 3 times m, m minus 1 plus 2. Okay, so the total Turina number. So the left-hand side, it's like the naive counting. So if you think about the double cover, so basically what's happening, I have a singular point, I resolve the singularity, so I introduce exceptional curves. And basically the total Turina number measures the number of this exceptional curve that I am producing during the resolution. Okay? So for my curve of C, and in the case that since we have only ADE singularities, this number is equal to something simpler. This is the total mean law number, and mean law numbers are well known. Yeah? So basically, it's sum over P singular of C. Let me call this mu P. So when I have ADE singularities, I know everything about these mean law numbers. I just look at these indices. Yeah? So when I have AN singularity, mean law number is basically this index. So when I have dn is the same, A6, A7, A8. So these are singularities with mean number 6, 7, 8. And I need to, this is basically no-brainer. I just, copy-paste numbers. This is magic. And this is basically based on Brieskorn theory on the formations of double covers. Persson is saying it's easy to see. Hirzebruch gave a proof, it's like 2 pages, extremely detailed, beautiful paper, and beautiful proof. You know, so let's say we're supposed to forget about Persson for this inequality, because this is really what Hirzebruch did. And then he defined, so basically, so Persson defined in his paper, definition, C, I should say in the setting as behind, but let's say if C satisfies condition that tau of C, or if you want, mu of C is equal to 3m m minus 1 plus 1, then C is called maximizing. So being maximizing is like only a sufficient condition to have the maximal possible picot number. Because still, you know, you have like a lot of -1 curves, so still you need to do like this secondary school thing, like compute the whether the intersection matrix is negative definite. You know, this is not guaranteed by this condition at all. So this is only sufficient condition. It's like, it's H11, or this is H11 minus H20. Yeah, so, yeah, this is H11, I would say. Yeah, yes, yeah. So this is H11 from that. Okay, so this is only sufficient condition, but still, you know, in many papers by, I would say, Dektiarev and many other guys, they're just saying maximizing means this. And we don't care whether like this, you know, the guys, or the guys span negative definite subspace, you know, that's the size of the negative definite matrix associated with this guy. Okay, so now I want to speak about derivations, because I don't want to speak about vector bundles, but let's say it's basically the same. So now I want to speak about free curves. But this is not a free in the sense of Mori, or nothing like that. So if I have a curve, reduced, S and F, so I have a curve of degree D, and then I define, so first of all, I want to define derivations. So this is basically okay, this guy. So I have like, but the point is here that these guys are polynomials, like, you know, not just, you know, coefficients, like complex numbers. These are basically polynomials. Okay, and then what I need is to define two objects associated with F. So the first object that I need to define is a set of derivations associated with F. Okay, so this object is defined as all those, you know, derivations such that if I apply this derivation to F, I am in the ideal, ideal span by this F. Okay, so the derivations preserving my curve, or preserving the defining equation of my curve. Okay, so this is rather standard object. And then, and I think it's due to Saito, around that moment, like 1980s, once again. And then we have a decomposition of this guy, since I can write, and now it's getting hotter, okay, because due to air conditioning. So basically, there's the composition. So obviously, I have this, I think this is called Euler derivation, yeah? So if I just apply Euler derivation Okay, let's this. If I apply this derivation to f, then I will get degree of f times f. Yes? So this is like the first natural derivation. It exists by you know, given by God. And then I have this part that is very interesting. This is d0. And d0, by definition, this is the set of annihilating derivations. Means that is the set of all these derivations such that so derivations killing my polynomial f. Okay? So I'm going to speak in a moment about vector bundles because I have to, but I have such a decomposition, okay? And now I want to define something, what is the free curve, basically. It's supposed to be German way of, you know, cleaning blackboard. Okay, so I need to define the curve that is free, so a reduced plane curve is free if, let me just use this guy only, if d0f is a free S module. And if you ask me, like, is it like common to be free? I would say very not. And there's like, basically, there's algebraic geometry behind this explaining why it's very difficult to be free. Okay, so, and for such a free curve, I need to define the so-called exponents. And exponents are going to be twists of a certain vector bundle. So now I'm just going to define MDR. And this is like cryptically looking minimal degree of Jacobian relations. And this is defined by minima over R such that d0fr is non-zero. So this is like the smallest possible derivation that, you know, killing my polynomial f. And I can basically write this d0 of f, and people are, you know, working with, like, you know, in the using the language of homological algebra, they're calling this RF, algebraic relations. So this is like a triple such that so this is basically the same, as you can see right now, yeah? So this is my derivation killing my polynomial f. And so this is basically, this is really like the theory of syzygies, yeah? If you think about it. So I have the Jacobian ideal, so I want to understand syzygies of this guy. And this is like the minimal, this minimal degree is like the minimal syzygy for this, you know, Jacobian, this Jacobian relations. Okay? And then, now I can define the exponents of a free curve C is a pair, and this pair is like okay, MDR of f, and this is n minus 1 minus MDR of f. Okay? So this is like a pair of numbers, right now looking somehow, it looks strange, but as a complete information, I need to understand 3 curves. And what we prove with n, I suppose to say 2n, or d, yeah, d. Yeah, it's supposed to be d. Thank you. D is degree. Okay? And this is what we prove with Alex Dimka, 2023. We proved that we have a plane curve, reduced plane curve, with ADE singularities of even degree, let's say d equal to 2 times m, and now it's like, if you would like to be coherent with K3 surfaces, I should say greater than 6, yeah? So greater than 6 is maximizing if and only if C is free with the exponents m minus 1 m. Okay? So this is our result. This is like if and only if, so you cannot do better. And why I am just saying, I mentioned something about these vector bundles. So right now, let me just explain to you why these curves are quite, let's say, rare. So if I have a standard exact sequence, so this is basically shelfification of the Jacobian ideal, okay, of my curve C. Then I have here 3 copies R of P2C, and I have a map given by the partials, okay? And here I have something interesting. I think this is called EC, so this is the sheaf of logarithmic vector fields along our curve C, yeah? Of logarithmic vector fields along C. And here, maximizing means that here I'm supposed to write right now to M, that this vector bundle splits as a sum of O of P2 C minus M O of P2 C minus M plus 1. Okay, so, the case when you have this splitting is, very rare. Yeah, so that's why we are just, we somehow, it's a kind of explanation why it's very difficult to find such maximizing curves. Because this condition is difficult to achieve. Like most curves that you are going to take, they are not free in this sense, obviously. So that's why I'm just saying it was quite surprising, because it explains somehow why, if you just try to search in literature, what are the interesting maximizing curves? There are not so many. Okay, so now I'm just going to give you some examples. I have this bazooka, it's very nice. I suppose that, how much time do I have? Maybe something like 20. Okay. Okay, so now the first example, some people are calling this Lagerfeld, I don't know why. It's by Persian. And this is partial triconical arrangement. Okay, so my C consists of three conics, like smooth conics. I'm just saying I am an explicit person, so I'll just give you the equations. So yeah. I have three conics like that. Okay, and now using bazooka, I will try to write this, draw this picture. Okay, so this is my first conic. This is my second conic. And this is my third conic. It's supposed to be alien. And then you have here two intersections. Very nice, like Lagerfeld, indeed. So A1, A1, A7, A3, A7, okay? So if you just sum this, this lower scripts, like, 7 plus 3 plus 7 plus 1 plus 1 is 19. So for D equal to 6, this upper bound, this tau of C, is less equal than 19, okay? If you just plug this D equal, okay, M equal to 3, which means D equal to 6, to this formula, you will see that the tau of C is supposed to be less equal, this global bound, less equal than 19. But in here we have exactly 19. So this is basically maximizing curve. And which is interesting, the associated K-free surfaces indeed has picot number 20. Yeah, so, yeah, because behind this, you're supposed to think you have a double cover, so you have a K-free surface, which means that this is like a really maximizing curve and the K-free surface has maximal picot number. And also, if you ask about moduli, this is the guy which is unique up to the project equivalent, so nothing interesting, This is like isolated guy. So this is about K3. Right now, something about Horikawa for jump. Okay, for Horikawa, which means that this is D equal to 8. Okay? So for D equal to 8, my upper bound tells me 37. Yeah? Okay, so what is the guy? So this is basically, I'm supposed to take this tricuspidal quartic, so the Steiner quartic. Okay. My wife is a painter and I don't have her genes somehow. I cannot draw anything. So then I'm supposed to take cuspidal tangents. Okay. And this is quite remarkable, I think, in classical geometry. These cuspidal tangents are intersecting at one point. If you are a symplectic geometer, like this four-dimensional guy, you would like to avoid this point, but I am not going to do this. And then I want to add line at infinity. And this is bitangent. Line infinity is bitangent. So what are the singularities? So I have 6 A1s. I have one, no, this is bitangent. 2 A3. I have one D4. And I have these three guys here, which are A7 singularities. So if I compute correct, it's like 6 plus 2 plus 1 plus, oh, this is even more complicated. So this is 6 plus 6 plus 4 plus 21 is 37. So this is another example of maximizing curve. If you ask me about curves of degree 10, there are some examples, like, 3, I would say, known examples in literature. And it shows somehow that these curves are extremely difficult to construct. Why? Because being ADE is like, you're supposed to reach the upper bound using small numbers. Yeah, because these ADE singularities have small middle numbers. That's why it's getting more and more complicated when the degree grows. So for these guys, for optics, for Horikawa, you can also use this Persian triconical arrangement just by add one additional conic, and you will have a Horikawa. This is another guy, and I think that there's also one additional guy. And this guy is constructed using this configuration of 4 conics having maximal number of tack nodes. Yeah, because you have this consideration by Meghesi, or I think also by Naruki in 1983. So how to construct arrangements of conics with maximal number of tack nodes. This is a completely different story, not for today. So if you would like to ask, what about how to proceed? I suppose to say wish you good luck trying, because it's complicated. Okay, so now I'm supposed to have 15 minutes. So I'm going to speak about combinatorial algebraic geometry. Okay, so now I'd like to speak about Terrao's conjecture. This is called numerical Terrao's conjecture. And this is conjecture about, it's somehow related to this maximizing curves, but this is for general, meaning that I want to have curves of even or odd degree, it does not matter. So I need to have a small preparation. So right now, I assume that I have curves in P2C, and I want to define something which is called weak combinatorics. This is arrangement. So basically, arrangement means for me that it's reduced. Okay? It's a reduced curve. And then weak combinatorics of C is defined as, this is a vector let's say KL okay, so this KI means this is the number, okay, so Ki is the number of curves of degree I, and I want to make my life very complicated. So I assume all curves are smooth. So because we want to be coherent with classical Terrao's conjecture, which is about smooth objects, so basically lines, this is it's a messy assumption. Your life is as complicated as possible. And then this, this hash Sj, let's say, is the number of singular points. of a topological type of a given topological type. Why this is about topological type? Because, you know, my curves are smooth, so somehow singularities are more or less determined by the intersection indices, yeah? And how they intersect. So, example, if this is line arrangement, oh, I can say even F. I mentioned something about complex numbers, let's say, over any field. So, weak combinatorics is basically D, meaning that this is the number of lines that I have, and then I just use Hirzebruch's notation. So I have T2 up to TD, and Ti is equal to the number of e-fold intersection points. Okay? And numerical Terrace conjecture tells us that if C1, C2 are curves with only quasi-homogeneous singularities, such that these vectors are the same and C1 is free, then C2 has to be free. Okay, so this is basically like, I'm just looking at the simplest possible invariance, combinatorial data that is associated with my two curves. Obviously, I assume that all components, irreducible components, are smooth, okay? So this is all the time the same assumption. And if they have the same vectors, like this weak combinatorics, then if one is free, then the second has to be free. If you think about it, it looks very suspicious, like there is no reason behind this. But this is like the problem in combinatorial geometry. So you look at the problem, it makes no sense, but it might be true. And this is more or less the case. And there are two results, important results about that. So the first thing is that NTC fails in the class of line arrangements. So there are counterexamples. So we have two line arrangements having the same three combinatorics. One is free, another is not free. And together with my co-authors, we basically proved that up to 12 lines, NCT holds. Then for 13, we have like several examples. For 14 lines, there is no single counterexample. And Jean Vallès and Simone Marchesi, they found a counterexample for degree 15, basically. So this is everything what we know about it. And together with Alex Dimka, this is my last result today, we proved something that we did not believe, but okay, so we proved that numerical Terrace conjecture holds in the class of conic line arrangements in P2C, admitting nodes, so A1 singularities, TAC nodes, A3 singularities, and ordinary triple points. So D4 singularities. And we have a complete classification. So the classification is like that. First guy, one tuck node. Second, third. These are basically tuck nodes, okay? 4. This is very nice. And, you know, we are in a good place for that. Even better. That's it. Here we have number of tuck nodes. As far as I remember, is, oh, let me just write like that. It's 5. This is a complete classification. Conic line, basically, I admit smooth conics and lines. Not really, because I would like to have at least one conic and at least one line, because, like, yeah, it's a good question, like, you know, let's say conic line enough means that you're supposed to have at least one line, at least one conic, because, you know, because this is like a degenerate case, you know, so you don't want to have this. And the problem is that why this numerical conjecture holds, all of those guys are unique up to the projective equivalence, and that's it. It holds because it holds. But you know, if you just look at this picture, that's it, like 5. And we thought this is not possible. Like, how is it possible that there are just 5? But anyhow, it also shows that this is guy of degree 5, 5, 7. So there is no maximizing curve consisting of one conic, or conics and lines with nodes, stack nodes, and ordinary triple points. So this is also like showing that, you know, because we wanted to find another guys, like another examples of sextics, maximizing sextics. But apparently, for sextics, there's a complete classification by Young, 1999. There's like Tohoku paper, and he basically showed that there's exactly 843 maximizing sextics, and among them 128 are irreducible. You know, and if you just ask me how this is done, by Nicolin's theorem. Basically, he used the K3 techniques, just this embeddings of, you know, lattices, like, you know, this famous theorems by Nicolin. So this is like computer approach. This is computer proof. Okay, 1999. Yeah, okay, also computer proof. But it has nothing to do with geometry, so he's not constructing anything. He's saying it exists because of Nicolin. So we have a complete classification. So I just look at this, and indeed, there is no sextic with nodes, stack nodes, and ordinary triple points. So it seems that our result is correct. Yeah, so because I learned after that, like 2 years after that, I say, okay, so let's hope that this is the complete list. There's nothing to add. Thank you for your attention. Yeah, there is like a sequence of such curves constructed by Persham. You know, it's like maximizing, meaning that satisfying the upper bound, or maximizing, meaning that you have associated surface with maximum pickup number. So there is, yeah. For either, yeah. So there's, I want to be sure that you listened. Yeah. So no, basically, this is a very nice construction by Persham, but this is the only one sequence that we are aware of. Yeah, it seems like that. So there's just one, and that's it.
The lower bound, the Persham lower bounds, that doesn't depend on the fact that the base is P2, it doesn't.
No, because if you just look at the paper by Beauville, he's just saying any surface, anything, like whatever you want. Like there is not like P2 specific, because we wanted to use these double cover techniques, you know, and because we thought that we understand, yeah. So that's why we use these double covers, and this approach constructing the surfaces using, no, this is what was done by Persian. That's like, I don't think so. You know, there's, if I remember Beauville's paper correctly, he's just giving examples, but you know, I don't think there is any kind of structure. I don't think there is any hope about, you know. Yeah.
For lines arrangements, there exists cytoscriptivity, right? That's how characterize.
Yes, there is a Saito characterization. Yeah, like full lines. Yeah.
What about in this context?
Yeah, this is interesting because, you know, Saito's conjecture is true for hypersurfaces in Pn. There's nothing about to do with line arrangement. Like if you just take Alex Dinka book, there's like the general Saito's criterion, and you can find it. This is chapter 6, I would say, or 7, 152 page, something around it. So you will see that it has nothing to do. Basically, this is a folkloric result. That, you know, Saito's criterion using this, you know, syzygies, yeah, so it's for any hypersurface.
And it's possible to characterize maximally?
In which sense, maximize? Yeah, because, you know, this is something specific for, you know, for our purposes, but, you know, because, you know, there's idea of maximizing, in the case of curves, maximizing like this total Turina number, yeah, in any degree, just not even odd, whatever. That's,
When you put some numbers in the equation, when you put a split, you put some numbers in the, right? In the split. M, I don't remember.
yeah, this is m minus 1m. Yeah.
It's somehow related with the degrees of the syzygies.
Exactly, because this is what I wrote basically. These exponents are degrees of the syzygies. So this is the same. Because, you know, this picture about vector bounds is basically shiftification. It's nothing, it's like, you know, it's basically saying modules, vector bundles, that's the same. So this is, you're right, this is the same numbers in the splitting type.
What is known about the other extremal case? So let's say tau is 0, for example, and the curve maximizes the critical number.
Tau is 0, it's a very good question. It's a question also by Beauville. We have no idea. Yeah, because this is the first question that Beauville asked, because we are aware of this, that you can just take a smooth sextic and you can construct a free surface with maximal pickup number. What about octaves? No idea. This is an open question. This is the question that Giancarlo asked me like 2 years ago. You don't remember, I remember that. I was in German. So yeah, so basically that's like the typical question, like also Beauville asked, you know, because we know that there are some maximizing smooth curves. So what about Horikawa case? But I don't know. Really don't know. I think this is a very difficult problem. Even, you know, in the case of sextic, okay, but for Horikawa it's terrible, I would believe. We know even how to start.